All right, here we go with Chapter 6, all about polygons. 6.1, we're going to talk about the properties and attributes of polygons. But before we get started, hey, Ms. Kupasek, what type of figure is like a lost parrot?
A polygon.
Why is that? Because it's gone. Polygon. Polygon.
Poly.
All right, so continuing on, we're talking about polygons this whole chapter. Let's actually define what a polygon is. A polygon has to be a closed figure, okay, and it's formed by a finite number of coplanar segments. Finite meaning there's an actual count to these, okay? So it's got to be a closed figure formed by a finite number of segments, coplanar segments, segments in the same plane. Rules: the sides have to have a common endpoint, and these cannot be collinear. So for instance, if I have a side here, the next side cannot be collinear, meaning it can't be in a line with the other ones. And then the next one says that each side intersects two other sides, but only at their endpoints. So if you have two sides, they can only intersect at the endpoints. You can't have something that looks like this and call it a polygon. So if we go through, think to yourself, is this a polygon, yes or no? Well, yes, it would be. It's a closed figure. There's no open spots, okay? They have common endpoints where the lines or the segments here are not collinear, and then we intersect two other sides, but only at their endpoints. This also is a polygon. This one as well. This one, if you think to yourself, we have an open side here, so therefore, since it's not closed, this is not a polygon. If you take a look at the next one here, this is not a polygon as well because, remember, we can only intersect at the endpoints. Here we're crossing. You cannot have segments that cross, so this is not a polygon. And then the last one is not a polygon as well. The reason why, well, we need to have segments. This here is an arc. It does not work. So polygons can be two things. They can either be convex or non-convex, which a lot of the times we will refer to as concave. Convex means that all of your diagonals are in the interior of the polygon. Concave is just the opposite. What I like to think of is convex has all of your vertices pointing out. Okay, all of your vertices will be pointing out. Concave, think cave, inside, you will have a vertex that goes into the figure. So this first one here is a good example of a convex polygon. All of your vertices are pointing out. If you put your diagonals in, all of your diagonals will be in the interior of the polygon. Okay. If you take a look at the next one, this one will be concave. One of the reasons is one of your vertices enters the inside of the polygon or inside of this shape. Also, if you put in your diagonals, you'll notice this diagonal, they go outside of your figure. This doesn't work, okay? All diagonals need to be in the interior, and then your vertices need to be pointing out. Okay, so I apologize for the pre-writing on this page, but for some reason my list, I'm not sure what happened to the right-hand side, but everything's shifted up. A polygon is also named by its sides, specifically the number of sides. Remember, the number of sides is also equal to the number of the angles. If I have a three-sided figure, you guys should know that the name of this is going to be a triangle. Now, a four-sided figure, immediately you think of rectangle, you think of square. This has a general name. These are called quadrilaterals. Five-sided figure is pentagon. 6 is hexagon. 7, heptagon. 8 is an octagon, 9 is a nongon, 10, decagon, like decade. Now 11 doesn't have a name, so we call it an 11gon. I know it's super creative, right? 12 has a name, it's a dodecagon, and then anything afterwards kind of follows what the 11 is. So like 13 ends up being a 13gon. You need to know these, the names of our polygons. You need to know if it's an octagon, that it's 8 sides. If it's a nonagon, it has 9 sides, or angles. You need to know these in order to do formulas that we will have later on. Okay, polygons are named by their vertices, and they're named in consecutive order. So for instance, this is a 5-sided figure, so we call it pentagon. And now we need to be in consecutive order with our vertices. So S, T, U, V, R. So this is pentagon S, T, U, V, R. All right, regular polygons. These are polygons that are convex with all the sides congruent and all of the angles congruent. I would like for you to think now, what figure has all sides congruent and all angles congruent? There are two regular polygons. What are you thinking? Hopefully, one of them that you came up with is a square. In a square, all of my sides are congruent. All of the angles are 90 degrees. The other figure is an equilateral triangle. Because in an equilateral triangle, it's also equiangular, making them 60 degrees at each corner. And then all of your sides are going to be congruent. So this is an equilateral triangle. All right, so we're going to classify these. First of all, by its sides, then tell me if it's convex or concave, and then tell me if it's a regular or not regular polygon. If you take a look at the first one, classifying it by the number of sides, well, this figure has 1, 2, 3, 4 sides. So you would write down that it's a quadrilateral. Okay. Next says, is it convex or concave? Well, all the vertices point out. My diagonals are on the inside, so this makes it convex. And lastly, is it regular or not regular? Well, if all the sides are congruent, that makes this a square. If it's a four-sided figure with all the sides congruent, it is a square, meaning that we have all the angles congruent as well. So yes, this is a regular polygon. Please pause me and try this second one. Okay, so what you should have noticed is that it had 7 sides. So that makes it a heptagon. Oops. We have one of our vertices going into the figure, making the diagonals not in the inside, so that makes it concave. And since all of the sides look like they're different, we're going to call it not regular. When we talk about our polygons, you guys, we're going to talk a lot about the sum of the measures of interior angles. Remember, interior means that we're looking at their angles in the inside here. So if I want to find the sum of the measure of the interior angles of a convex polygon, we can do this a couple different ways. First, I want to start off just by simply drawing our diagonals from any vertex. So let's take a look here, and I'm sorry this happened to this chart. It kind of got a little bit smaller. If I were you, I would extend this out that way. Give yourself some more room. So we're going to start with number 3, the number of sides being 3 sides. If I have a 3-sided figure, we're looking at a triangle here. If I want to draw in my vertex, or lines from my vertex, what happens is you end up with something that looks like this. Okay, the number of triangles that we see, well, duh, that's 1. Okay, and the sum of the measures inside of a triangle, you guys should know, is 180 degrees. You can see why I wanted you to make yourself have more room. All right, let's move on. This is our 4-sided figure here, a quadrilateral. If we start from one vertex and draw in our diagonals, we have 1 there. There we go. Okay, so if you take a look, we end up with 1, 2 separate triangles. And if I add up the total degrees inside of these 2 triangles, I have 180 here, 180 here, leaving us with 360 degrees. Okay, so 3 sides gives us 180 degrees. 4 sides gives us 360 degrees. Okay, remember we've got 1 triangle here and 2 triangles here. Go ahead, I want you guys to do these next 2, kind of fill in your chart. So pause me, do these next 2, fill in your chart. We'll see if we end up with the same answers. Okay, so what you should have noticed, is that when you draw in your diagonals, if we have a 5-sided figure here, we end up with 3 separate triangles, giving us a total of 540 degrees. And if you look at your 6-sided figure, we end up with a total of 4 triangles, giving us the 720 degrees. So if you take a look at this, this is really nice, neat, it's convenient. However, what happens if you end up with a 15-sided figure? I don't know about you guys, but I don't really feel like drawing in all these little triangles all over the place. So the easiest way we want to do this is to come up with some sort of a formula. And if you look at this, what happens from each time is the number of sides. To figure out the number of triangles we have each time, you should have noticed the pattern is we take away 2. From there, if we multiply by 180 degrees, we can figure out the total sum. So just like we said before when we were drawing in our triangles, if I want to find the sum of the interior angles, all you have to do is take the number of sides, that's n, subtract 2 from it to give me the number of triangles inside of this figure, and then multiply it by 180 degrees. So in this first example, if I ask you to find the sum of the measures of the interior angles of a heptagon, well, the only thing you really need to know is how many sides a heptagon has. If you realize that a heptagon has 7 sides, we can plug it into this formula, 7 minus 2, and multiply it by 180 degrees. That gives me 5, multiply it by the 180 degrees, and you get the sum of the interior angles. Okay, so what I would like for you to do now is do this next example, so pause me. Use this formula, please, it's going to help you out. And in this case, I'm asking you to find the number of sides if I give you the sum as 7,020. Okay, when you plug this in, obviously where S is, we want to take our 7,020, plug that in there. Now my goal is to find N. So our first step would have been to divide by 180. That cancels it out on the right-hand side, leaving you with 39 equals N minus 2. So your number of sides, when I add the 2, is 41. Alright, so now if I ask you to find the measure of each triangle, not the whole thing, not all of them together, not the sum, but each triangle, you're going to take that sum formula and then divide it by that number of sides to find each individual one. So if I want to find the measure of each interior angle of a decagon, well, the first thing that you have to think of is how many sides does a decagon have? That's 10. All you have to do now is plug that in for your n. So one angle is 10 minus 2 times 180 over 10. Okay? If you work this out correctly, you will end up with, what is this, 8 times 180 over 10? Giving you 144 degrees for each one of those angles. Okay, I would like for you to pause. Please do the second example. Alright, so in this case, they gave you the actual angle measure, so you plugged it in over here where we have the one angle. Now if I want to solve for n, you're going to have to do some shifting. To get the n out of the denominator there, obviously you would multiply. Now I have 140n equals, if I distribute this, you get 180n minus 360. Okay, doing some simple algebra here, moving and shifting things around, we get negative 40n equals negative 360, leaving you with your number of sides being 9. Alright, so this whole time we've been talking about interior angles, but when it comes to polygons, we not only have our interior angles, but we have exterior as well. Okay, so if you take a look at this figure, we have both of them. We have our interior angles, and they're paired with our exterior angles. If you look, if I wanted to know the sum of all of this together, well, if I have an interior angle and an exterior angle, they create a line making this 180 degrees. If I wanted to know all of this together, all I would have to do is take 180 degrees times however many vertices that we have, giving us the 180n. But I know the interior angles. I know it because we just did the, the formula to figure out what each interior angle and the sum is. So if I just want to find my exterior angles, all I have to do is take the whole thing, which is my 180n, and get rid of the interior angles. We know the interior angles is n minus 2 times 180. I would like for you to use your algebra magic, please, and actually solve to figure out how I find the sum of the exterior angles. Okay, so what you should have noticed is after you distribute the 180 degrees, when I change my signs because of this negative out front, these 180 ends end up canceling each other out, leaving you with just 360 degrees. This should make sense because as you start closing these exterior angles, you'll notice where you started from, you come right back around and end at, creating a figure that looks like a circle. And how many degrees are in a circle? 360 degrees. So your exterior angles, the sum is always going to be 360 degrees for every polygon. Okay, so this is just officially telling you that the exterior angle sum theorem is that all the sums of the exterior angles for any polygon is 360 degrees. So if I ask you, find the sum of the exterior angles of a nonagon, well, who cares how many sides it is? The sum for any polygon's exterior angles is 360 degrees. Just like when we did one interior angle, if I wanted to find one exterior angle, well, you'll take the whole thing, the 360, and divide it by the number of sides, n. So if I ask you to find one exterior angle of a decagon, remember decagon has 10 sides, you'll take your 360, divide it by 10, you'll find that each one of my exterior angles is 36 degrees. All right, so overall, you need to know this chart here. If I'm talking about interior angles and the sum, this is our formula that we use. The number of sides minus 2 times 180. If I want each one of my interior angles, I take that sum and I divide it by n. Okay, if I want my exterior angles, irregardless of the number of sides, it's always going to be 360. And if I want one of them, I have to take that 360 and divide it by n again. Know this chart, please. You'll have to fill this in at some point. Remember, n is not only the number of sides, but also the angles inside of your polygon.